Hello, my name is Ramsey Alsheikh, and welcome to my project titled Natural Computational Entropy in Random Number Generation. What are random numbers? Random numbers are numbers that are generated in such a way that it's practically impossible to predict what they are going to be beforehand. You cannot know what you are going to have after the program runs. There are two kinds of random number generation. There's true random number generation, which observes like external processes and uses the results of those processes as the basis of generating numbers. So for example, if you observe a quantum mechanical situation in physics and you take the output, which is impossible to predict according to the laws of quantum mechanics, use that for generating numbers, that's true random number generation because you're observing something. Pseudo random number generation is when you use an algorithm, just a pure mathematical function to give you random numbers. So you give it a number and it'll give you a spread of numbers that are so like spread out, and it looks like there's no pattern between them, but in reality, there's some complicated algorithm that's generating them. The number you give it, by the way, is called the seed. What is Die Harder? Die Harder is a suite of statistical tests that verify if numbers are random, or if they're likely to be random. I came up with the idea for this project after reading an article where I read that the world loses about $5 trillion every year due to cybercrime. So I started thinking about ways we could prevent that and make and improve, modern cybersecurity techniques. And I read that random numbers are actually very useful in online transactions because you can encrypt things according to random numbers so that hackers can't, predict what the key is going to be to unlock what you're sending through the internet. So I thought of ways to improve it, and I came up with a more affordable and accessible way to generate random numbers. And it uses a concept I call natural computational entropy. What natural computational entropy is, it's the idea that computers are so sophisticated nowadays that it's almost impossible to predict what they're going to be doing at any given moment. They're performing millions of calculations per second. Each calculation depends on the results of a million other calculations in the past. Each calculation there depends on so many different factors in the computer, because computers are so complicated and sophisticated nowadays that I thought that if we use that, we could generate random numbers that will be verified by Die Harder to be random and useful. The design of this project, I decided I would use a CPU, the CPU's register. A CPU is a type of processor located in every computer, every modern computer. And these CPUs, if you look, I have a picture on the last slide, have little memory banks called registers. They hold, they hold numbers for the computer while it runs through its calculations. They're kind of like a scratch paper if you're doing a math test. That's what a register is. They change their contents millions of times per second along with the computer. So they were a good choice as a starting point for a random number generator. My research plan would be to develop a random number generator in C that would get access and permission to go to the registers from the computer internally, go to the registers, read the values, use that as a starting point for a random number generator, and then give me a 32-bit base 10 number. So a number in that range. I had some challenges because I was working with very basic, when I say basic, I don't mean easy or simple, I mean very essential and fundamental hardware. That's kind of what the program was going to be. And then for my procedure, I would have my random number generator generate a text file of random numbers, give that to the Die Harder program, and then it would give me the outputs of its tests to tell me if the numbers were likely to be random. The independent variable in this experiment was the output text files being used. So I would generate multiple text files with my programs, and I would use each of them as output. And I would take this output for that independent program and use that as the independent variable. The dependent variable was whatever Die Harder outputted. So I would give Die Harder my text file, that's independent, and it would give me the test results, that's dependent. The control variable would be the default random number generator in C, programming language I was using. C it's an extremely popular, has a lot of history. It's a very well-known programming language, and the default generator on it is high quality. The experimental variable would be the generator I coded, the one I made that uses natural computational entropy. The constants, the starting point of where I ran the programs, where I ran them from, the operating system. I used Ubuntu Linux for this entire project and never changed it. I could not control the temperature of the environment. I couldn't control exactly what the computer was doing at any given moment, which is part of the randomness. I made sure it was on a good charge. I made sure it didn't overheat. Now, when I was actually implementing it, this slide is about implementation. I coded my number generator. I tried to keep the control and the experimental as similar as possible, except for the fact that my program would use the registers just to eliminate external, any miscellaneous variables that could come up. I let my programs run overnight. I took 3 trials from each. I gave it to Die Harder. I got my results. There were no changes made in between the planning and the implementation phase. The results. What you're seeing here is actually a list of p-values. What p-values are, they're a number from 0 to 1 that tells us how likely the numbers are to have been generated by a pattern, to be not random. So if the number is very, very close to 0, so if it's 0.0000 whatever, or if it's very close to 1, 0.9999 whatever, we failed. That's bad. If they're somewhere in between, that's good. You can see most of them are within a good range. It's only if they're very close that's bad. This one here, this was not a successful test, but the rest were. Most of them performed very well. This is just a widened version. You can see the specific Die Harder tests on each side. You can see the actual number I got. I put it in a bar graph. These are all of them. They're a little hard to see, but the gist to get from this is that they're all relatively in the middle. They all average to be about the middle. This is the control. This is the experimental. They perform similarly. They look similar. That brings us to our conclusions. The control was a well-known and established random number generator that's accepted. It's a good standard. And the one I coded performed very similar to it. This provides evidence for that the random number I generated is as comprehensive and as unpredictable as modern technology, meaning the hypothesis was supported, and we actually can use natural computational entropy to generate random numbers. The Die Harder test perform many different tests. As you can see, there's a whole list of them on the side. There's like 30 something. So we've been testing several different metrics, and the vast majority of them we passed, meaning random. This is the first success in natural computational entropy. It's a new concept that this is providing evidence for. The applications of this project, why natural computational entropy is so useful and why I believe it is borderline revolutionary is because it's accessible and it makes use of something ubiquitous to all computers, which is the CPU. Every modern computer, whatever you're watching this video on, I would bet you that it has a CPU. All modern computers have them, and all modern CPUs have registers. These registers are just one source of natural computational entropy. They're free to access. There's no external cost. You don't need research grade lab equipment to observe them. You just need a computer. There are no additional costs to access them. They're accessible, they're local. Anyone can use them for free. Additionally, the software to access them, I published for free. It's on my GitHub. There's a link. Natural computational entropy is extremely easy and free to use. Now, this improved accessibility translates to improved technology in cryptography, in the field of cryptography, and encoding numbers, because you use random number generators as kind of the key to unlock the password, so to speak. You can use them, for example, and this brings me to my next point, in online transactions, for example, online shopping, anywhere where you're transmitting secure information over the internet, you can use these random numbers to be a sort of, you need the random number to guess to get the contents of the letter. And if you don't know the random number, because it's unpredictable, you can't generate it. So that's the applications of random numbers. They have internet cybersecurity applications, and natural computational entropy is an aspect of random number generation that improves it in what I believe to be a radical and meaningful way. So that's kind of how we would apply this project. Thank you for listening to my presentation and watching my video. Have a good day.